of his talk is Episodes of Enhanced Carbon Sequestration from the late Barmarian early active.
Thank you everybody for being here. Most of you are familiar with this presentation because I went over this in the symposium. And yeah, it's about carbon sequestration in the late Barrenian and the early Aptian because we want to understand what factors are involved in this carbon sequestration and the fact that we have black shells and sometimes in some places we have black limestones and they are indicative of high concentration of organic matter. We want to see what factors are involved in this occurrence of these events. So here we have the main research motivations. There is a main oceanic anoxic event that is being well documented and described. But before this event, we have positive excursions in the carbon-13 here in the stabilized stones, as you can see in the red circle. And after this event, on the other side, we have also these positive excursions. They are indicative of there is carbon being sequestrated because what it means is that C12 is being intaken by organisms in a higher proportion than in normal conditions. So that produces that it depletes the reservoir, so the amount of C13 that is in the reservoir increases, and then we have these excursions. So that's the main motivation because we want to understand how this carbon is being sequestrated. And the significance of this research is that it's going to provide insights about the gradual response of different environments, especially these semi-enclosed basins, to warming conditions. When you have global events, how these environments they respond, and also why do we have in the late Barrenian early Aptian all the way up to the middle Aptian, 125 million years ago, these black shells and black limestone with high concentration of carbon. And also it will improve our knowledge about the response of these basins to increasing greenhouse conditions that we have today. So the study area that we're using for this research is located in the Spanish Pyrenees. It's an ideal place because as you can see here, the section is very expanded here and it's very well defined. You see the beds, the strata is well defined, and also this is a close-up of this section. You can see that the color here is black. It's not as the kind of rocks that we see here in Florida, which are white. In this one we have black color, and this is one of the indications that probably we have high concentration of organic carbon in the rocks. So for the development of this research, we designed a methodology that includes carbon geochemistry. We're measuring the TIC, what's the carbon content of this rock. We're measuring the TOC, what's the organic carbon content of these rocks, and also we're analyzing the stable isotopes, especially carbon-13 in the organic matter of these rocks. We also did microscopic analysis using petrographic and SEM. We look at the samples in SEM also to see what's deeper in the matrix at nano and micro scale. And here we did also major and trace elements analysis. Why? Because the major elements account for the origin of the sediment that we have there. Is an explanation of the clastic, where these clastic sediments are coming from, and if they're related to the amount of nutrients that we have in this basin. And also we are using the trace elements because the concentration and ratios of different trace elements, they explain how the reducing conditions are in the basin. If we have more oxidizing or reducing conditions in that basin. And finally, we use biomarkers to see what's the origin of organic matter that is being concentrated in these rocks. And the results, as you can see here, we built a simplified stratigraphic column that is showing what's the fossil content of different levels of this stratigraphic column, and also the variation, the vertical variation of the TOC correlated with the TIC and also with the stable isotope of carbon, the C13. So we identified 5 important intervals. These intervals are characterized by especially low abundance of benthic form. The concentration of organisms that live in the bottom of the sea at these levels is very low. And in some places, like here, they are absent. So that means something. Why do we have these events at these levels, and why do we don't have these benthic organisms living there? And also we see that we have, at these levels also, we have the highest peaks in the TOC, in the organic matter concentration at these levels. And also they're coincident with peaks in the delta C13. So all of them together accounts that probably we have higher biological productivity, because higher biological productivity will produce enhanced intake of C12. So with time, this organic matter will become enriched C13, and depleted in C12, and at the same time, if that's the case, it will consume the oxygen in the water column, and the conditions will become more towards the desoxic and oxic environment, and you have higher preservation of organic matter because of the lack of oxidation. So that's the idea that we're looking for to explain in this research. So first, we wanted to identify why do we have this high TIC. The carbon content of these rocks is very high. So we did SEM analysis, and we discovered that these organisms are present along the matrix of the rock everywhere, in any level. So they are in very high concentration. In some places, they are more than 1,000 in 1 centimeter. So it means they're highly abundant. So the TIC can be explained by the high concentration of these organisms. But in addition to that, we found something that is called pyrite. This is framboidal pyrite. This framboidal pyrite is an indication that we have reducing conditions in this basin. Because if you have oxygen available, the iron would be oxidized. But instead, here we have iron sulfide. So indicates that we have places that probably we have reducing conditions. How intense are these reducing conditions? We're trying to explain this with the trace elements, as we can see. So after that, we know the TIC where it's coming from. So we wanted to know why do we have this such high concentration of microfossils, calcareous fossils in this case. So we built these comparative to the diagram where you have aluminum, silicon, and titanium. Those are major elements that are related with continental rock. They are highly concentrated in the continental crust. And if you have them in your sedimentary rocks, it means an indication that you have a lot of terrestrial input. What's the amount of this terrestrial input? Well, it's related to the variation in the curve, as you can see here. But interesting enough, what we have here is that the concentration of phosphorus and iron, they mirror with different scales. Of course, the same behavior of the aluminum, silicon, and titanium. So it means that what is providing the nutrients to the basin is terrestrial input. So you have a lot of terrestrial input bringing nutrients to the basin, and that's why it drives primary productivity. And that's why you have this calcareous fossil being produced in such amount. So after that, we wanted to know also what's the origin of this organic matter. Because this fact that we have a lot of calcium carbonate being produced is not an explanation for the amount of organic matter being deposited. So we did biomarker analysis. We produced in 24 samples, and all the alkanes that are higher than 25, they belong normally to terrestrial organic matter. But as you can see here, nothing goes over 21. So here we have one approach. All the organic matter that is produced in this basin is autochthonous, means it's being produced in the basin itself. It's not coming from elsewhere. But the fact that we have calcareous nanofossils is not enough to explain the TLC higher than 1% that we have, because these microfossils, they produce more calcium carbonate than organic matter. So we wanted to explain what happened in this case. We have an option. We have bacterial productivity. So that's why we examined the samples in a deeper way, and then we identified these structures. These are structures, and this one here is amorphous organic matter. So what it means is these structures are being related before elsewhere with bacterial productivity. So they are characterized as bacterial remains. So that explains why do we have this amount of organic matter being produced in the basin and being deposited at the same time. Some of these bacteria can thrive in places where you have reducing conditions, where you have sulfur, and they can be denitrifiers, as we saw in the last seminar. So that some of these bacteria, they like environments where you have a slightly anaerobic or anoxic conditions, and they can live in those places. And then, to analyze if we have these reducing conditions, we use trace elements. We use ratios that has been used before to see what happened to these elements at those levels, and they agree very much with what we were saying. Here we have these peaks at these levels, and they indicate that we have reducing conditions. How strong are these conditions? They do not appear to be so strong because we have some levels, some benthic foraminifera. If they were anoxic, completely anoxic conditions, benthic organisms will not be there. So that's the case that we have. And same thing happens with uranium and thorium. vanadium, chromium, and nickel, cobalt. Vanadium, chromium never goes above the line that indicates reducing conditions, but this can be explained by continental runoff because the chromium is highly concentrated in the continental crust. If you have non-chromium incoming, the ratio will be smaller. So that's what happened. Also, we produce these ratios of pristine phytene, which are being characterized when you have these ratios less than 1, you have anoxic conditions. But this is not exactly. You have to use comparative approaches to tell if you have anoxic or disoxic conditions. But the fact that we have all these ratios, less than 2, most of them, indicate that most of these environments is at the time of the organic matter being produced, they were slightly anoxic, not completely anoxic. So that indicates that we have an environment where it's organic matter being produced, carbon is being sequestrated because it's being locked in the rock, and at the same time, this environment is slightly reducing, but it doesn't get to strong anoxic conditions as we were expecting. So, as conclusions, we have that terrestrial fluxes is what drives the primary conductivity, and the high TUC values at the positive expressions are related to enhanced sequestration of carbon and these basins, and you have oxygen-restricted conditions, and the high TUC is the result of these calcareous fossils being produced in such a huge amount, and the organic type of basins can be important organic carbon sequestrators, and at the same time, they can be, if you have the right conditions, they can be potential hydrocarbon source rocks for the future. Okay, thank you. If you have any questions.
So that was 11 and a half minutes. You guys are all perfect, so we have plenty of time for questions.